Good evening, students. Today's topic is effect of dielectric on capacitance. Clear? Let us discuss. Suppose in between the plates of a parallel plate capacitor, I placed one dielectric or insulator inside it. So what is the effect on its capacitance? We will study. Before going into its entire effect, I need to recall some of the ideas of the previous classes. We know the formula for capacitance is C, which is equal to Q by V, where Q is the charge given to the capacitor plate. V is the potential difference between the plates of the capacitor. From this formula, already I have discussed, keeping the Q constant, if anyway we can change the potential V, potential difference V between the plates of the capacitor, this is going to affect your capacitance. Means if you decrease the potential, then the capacity there is a chances to increase. So in a small space we can store large amount of electrical energy. Now V is related to the electric field by this formula. We know E, the mod of E, magnitude is given by dV by dr. dV is the potential difference, dr is the distance. Now in this case, for a uniform electric field like the field inside a capacitor, dV I am taking it to be your V and dr to be your d. D is the separation gap between the plates. Now in this figure, E is related to your potential difference. If we want to increase or decrease the V, the same way it will affect the electric field inside the plate of the capacitor. Clear? Means if we want to decrease the value of V, we need to decrease the value of E. Try to remember. Means if V decreases, C will increase. To decrease V, we need to decrease electric field. Clear? So to decrease electric field, let us see what a capacitance, what a dielectric is actually doing here. What is the role of a dielectric? Let us come to this figure. In your earlier classes, I have already discussed, if inside an electric field, external field, here it is denoted by E naught, if a dielectric is placed, the dielectric gets polarized in the presence of external electric field. This is your figure of polarization. Here the external field is given by E naught and there exists another field, means that is one kind of field is developed inside the dielectric because of this polarization, means charge separation. And that field is denoted, it can be denoted by your polarizing field, that is EP, or that is called field because of your dielectric polarization. Now whatever the net electric field inside the dielectric is the effect of the two field. One, this external field, another one, that is the field because of the polarization. Now the net field inside it is given by E naught minus EP. E naught is the external field, EP is the field because of the polarization. Got it? From this expression it is clearly visible, E net is less than that of your E naught. If only air gap will remain inside the space of a capacitor, the field would have been E naught. If a dielectric is placed in this space, the electric field is reduced to E net, which is less than that of your E naught. It means by placing a dielectric in the region of an electric field, we can reduce the electric field, so also the potential. That will affect the capacitance. That is our main aim. Now let us define this term. If E net is less than E naught, then E naught by E net is equal to K, that must be greater than 1. This K is a term that is called dielectric constant. So we can write E net is equal to E naught by K. Clear? This value E net is the net electric field inside a dielectric. So the net field decreases by K times inside a dielectric. Means if you decrease the field, we can decrease the potential, we can increase the capacitance. how let us devise or let us derive a mathematical formula where we can see actually what is the value of that capacitance. For that reason, I took a parallel plate capacitor, two plates here. Here, I have not shown pictorial presentation of the fields here. Only I have written the field whatever exists there. I took two plates of a parallel plate capacitor, which is A and B here. The plate separation is D. I took one dielectric of dielectric constant K and thickness is T. As I have already said, as this is the air gap and the air gap amount is D minus T, because the total separation is D and this separation is T, so it is D minus T. In between this gap only your E naught is there, means the field of a free space or approximately that of air gap. And within this, as it is a dielectric and it will get polarized like that, so the field will be E net here. Got? So now our aim is to calculate the capacitance of this arrangement. So in that case we need to calculate V. To calculate V we need to apply this formula. So now V means the potential difference between the plate A and B. So VAB we can write here, VAB, let us take it to be V, which is the potential difference between these 2 points and potential difference plus potential difference between these 2 points, means VAB is equal to VAC plus VCB, where see now you can apply that formula. VAC, AC is the air gap and the span of the air gap is D minus T. So according to our formula, V is equal to E into D, that's a general formula. So in between, since we are finding the potential difference between this air gap, so the potential difference V is equal to the field. Field here it is E naught into the gap is D minus T. That's what it is written here. For VAC it is E naught into D minus T, because that much air gap is there, plus VCB. CB is the potential difference across the dielectric, and that since the field is there E net, so your VCB is equal to E net into the thickness T. Now comes to your V. So here, and we know we can substitute for E net. Here already I have derived E net is equal to E naught by K. So E net is equal to E naught by K. I have just substituted E net in this expression. Now from these two expressions, E naught is a constant, so I took it out. So your expressions will be E naught whole into, here it is D minus T plus here it will be T by K. So V is equal to, V is given by E naught D minus T plus T by K. And you know E naught is what? E naught is the field in between of the parallel plate capacitor and that having air gap, and that for that E naught in your earlier classes I have already derived, it is sigma by epsilon naught, where sigma is the surface charge density of the parallel plate capacitor. So for E naught I have substituted, which is sigma by epsilon 0, and it is D minus T plus T by K. Got? And we know sigma is what? That is Q by A, charge per unit area. So for sigma I substituted, which is Q by A epsilon naught, and this term remains as it is. And we know the formula for capacity is Q by V. Now we put the value of V of equation 2 and put it in equation number 1. So after putting, I am getting C is equal to Q by V. Instead of V I am writing Q by A epsilon naught whole into D minus T plus T by K. Now Q got cancelled and I am getting the value of C to be epsilon 0 A by D minus T plus T by K. So this expression is most important because see here this dielectric is filling the gap of the parallel plate capacitor to some extent. Question may ask if someone will fill the gap completely. So in that case your expression can change. If someone will change the entire gap, means your thickness of the dielectric will in that case will become your D. In that case you can substitute T is equal to T in this expression and you are going to get that capacity. Let us mark that capacity to be C dash. C dash will become epsilon 0 A minus D D minus, instead of T I can write D, because T is equal to D, as this gap is completely filled by the dielectric. So D minus D plus, again here it is T, instead of T I will be writing D by K, and here D minus D is 0 and D by K. So epsilon A by D by K will be your answer, and your final answer C dash would be how much? It would be epsilon 0 A by D by K, or you can write K epsilon naught A by D. This is the value of your C dash. Now, if only air gap would have been there, we know the formula. If only inside a parallel plate capacitor having only air gap, we know that formula of capacity, which is given by only epsilon 0 A by D. And if this capacitor is filled totally, completely by a dielectric, then its capacity becomes C dash. If a dielectric fills the gap completely. So C dash becomes K epsilon naught A by D. Now you see here, C dash is equal to K into C. C dash, because epsilon naught A by D is your C. So C dash is equal to K into C. And already we have told the value of K. The value of K is greater than 1. Since the value of K is greater than 1, which implies we can say C dash is greater than that of your C. It means the capacity of the capacitor increases K times if what the value had was earlier. C is the value of the capacitance when only air gap was there. And now C dash is the value of the capacitance when that air gap is filled by a dielectric of dielectric constant K. It means from this expression we can prove that the capacity increases with the introduction of a dielectric in between the gaps. See students, just now I have told you the formula C dash is equal to K into C. C dash is the net capacitance inside a dielectric filled capacitor. So here, depending on the value of K, your capacitors are of n number of capacitors there. Like it can be a paper capacitor, it can be a mica capacitor. Like it means in between the plates of the capacitor, you will take a paper sheet. Then that will give you a definite of capacitance. So basically, our aim is to increase the value of K. K means dielectric constant. It is otherwise called your what? Relative permittivity. If you increase the relative permittivity of a material to a very high amount, so we can get higher value of the capacitance, and the research is being going on in the branch of your material science. The materials are being developed to increase this value of this K, so that we can get larger value of the capacitance within a very small space. That is the present aim of your material science, and they are doing it. Got it? So, and as that day we have discussed, your farad is a very bigger unit of capacitance that they have told, because to have a capacity of 1 farad and your radius of that object, if it will be an isolated sphere, it would be much more than that. That means 1000 times greater than, more than 1000 times greater than that of your earth. But if we use this method, so we can increase the capacitance to a very greater extent, and we can get the capacitance. But 1 farad is a very bigger unit. So with the capacitance what we are using in our day-to-day life, it is of the order of your nanofarad, microfarad, picofarad, and your femtofarad, like that. Got? And actually capacitor is a very vast role in our day-to-day life, starting from your mobile phones to the fans to TV and all the electronic devices. We are using this capacitor.